Hi, today I'd like to go over some more details about reflection and refraction, hopefully explain some of the things you noticed in the PhET simulation yesterday. So as a quick review, the difference between reflection and refraction is reflection is when light waves bounce off of a surface, and refraction is when light waves go through a surface but are bent in the process. And today, hopefully, after this lesson, you'll understand why it bends just a little bit. So to start, we'll start with reflection and how physicists talk about the angles. This is where I wish we could have been in school, so we could have done a lab with measuring angles, but instead of measuring angles with relation to whatever surface they're hitting, they measure angles in relation to what's called the normal line. And that's basically, it's an imaginary line that's perpendicular. So if this is your surface, your normal line is like this. And one thing the normal line basically does, as you see in all of these examples, I didn't draw the surface, is here, but it basically cuts the path in half. So it's equal angles on both sides, which is one of the key findings from yesterday. So real quick, just a few more words. You'll see this symbol. This is the symbol for an angle. I stands for incidence, or the incoming light. And the angle of incidence is from the light ray itself to this normal line. And if you were to use a protractor to measure, the angle of reflection is the same angle. And that is always the case. We could use our simulation. Oh, spoiler alert. Oh, well. Let's put this back up to water. So this is our line of reflection, and if we're coming in at 30 degrees, our angle of incidence is 30 degrees. Our angle of reflection is also 30. And if we go down to 60 degrees, then our angle of reflection is also 60 degrees. Yeah, so those angles will always be the same, which is kind of cool. Then you also have the angle of refraction. And so this, once again, is between the light that passes through and the normal line. So in this case, the angle of refraction is less than the angle of incidence, which means that the light is bending as it goes through the surface. And we can see that here. If I come in at 60 degrees here, 60 degrees angle of incidence. Down here, the angle of refraction is only, it's a little less than 40. Yeah. So the question is, why? Why does it seem to bend? And why do different materials, like, so that's water. So if it was air, there's no bending. But if it's water, it starts to bend. And if it's something like glass, it bends even more. Why? So this is because light moves at different speeds depending on the material it's in. And this has to do with the density of the materials. And so the way to imagine this is like imagining you are mowing the lawn and you're moving from the sidewalk to the grass, and you have like a mower that turns on its own, like a powered mower. I don't know if this analogy works. I've never actually tried this. It's also like tank controls if you play video games or have driven a tank. But the basic idea is you have your lawnmower, and both sides of the lawnmower are moving at the same speed as it moves down. But then as soon as it hits the grass is thicker, and it like makes the wheel turn just a little bit slower. So you're in this situation where you have one side of the lawnmower going slower because it's in the grass, while the other side is still out on the sidewalk going faster. So when you have like one side still going fast and the other one starting to go slow, instead of going together, one starts to do this and you get this turn. So as it hits this thicker material, it starts to slow down while the rest of it keeps going fast and it causes it to bend. And the same thing, the opposite happens when the lawnmower leaves the grass, when we go from a thicker material to a thinner material. In this case, the wheel hits the sidewalk first and it starts to speed up. And when one side starts to speed up, once again, it bends it that way. And this can lead to all sorts of crazy effects. It gets complicated real quick, and I'll leave the research into like why this happens up to you. Optics is crazy stuff. All right, so your reference tables. How can your reference tables help you with this? So first, at the very front of your reference table, we have the fastest speed that light can possibly be, and that's the speed of light in a vacuum. In a vacuum, there's no matter, there's no particles, there's no nothing, and so those waves of energy are completely unhindered, and they move at a rate of about 3 times 10 to the 8 meters per second, 300 million meters per second. Is it 300? Did I just do my math wrong? I don't know. I think it's 300 million. It's not 30 million. Yeah, 300 million. Tell me if I'm wrong in the comments. Like and subscribe. Smash that like button. So that is the speed of light in a vacuum. But on Earth, we don't live in a vacuum. We live in air and water and other materials. So as the light hits different materials, it slows down because those materials have different densities. So depending on the particles are made up of and how tightly packed they are together, the light slows down. So the light, this is basically like a multiplier. Like we're not going to get into the math of it. If we were in school, we would, but we're not. So we're going to keep it to conceptual. And what you need to know about this table is that the bigger the number, the slower the speed. That number, it's like it represents the difficulty the light has in moving through it. So the lower the number, the easier it is. As in when it moves through air, it's almost no different. But when it starts to move through like oil or quartz or any of these things, it starts to slow down. Your assignment on Castle Learning, like Regents questions, will refer to this table. So in your reference table, it's on the second page, and you'll need to maybe look to see how the numbers compare. It'll go faster when the numbers are smaller. Also for your reference, you have this diagram of the electromagnetic spectrum. One thing to keep in mind about this is all these different types of electromagnetic waves, X-rays, gamma rays, visible light waves, radio waves, they all move the same speed. Like they're all forms of light, like electromagnetic radiation. They're just, some of it is light we can't see. So they would all move at the same speed in space, or the same speed through air or anything like that. The difference between them is their wave lengths. Some have very long waves. 10 to the 4 is like, what, 10,000 meters long. That's huge. All the way down to very, very tiny waves. Invisible light is on the small side. So up here, you can see the scale of their wavelengths, and it's getting bigger and bigger and bigger as you go to the right. And down here, you get their frequency. And the weird thing about this table is the frequency gets bigger as you go to the left, but that makes sense. As the waves get smaller, the frequency, how many waves there are, gets more and more and more. Like little waves are, there's tons of them. Okay, so that's the reference tables. The big one you're probably gonna need is this. So yeah, one last time, the higher index of refraction means it's a slower speed and a smaller wavelength. We can actually see that when we switch over to this. They're drawing it as a longitudinal wave. This looks more like a sound wave. They're not drawing the transverse waves that we know they are. But once again, it has to do with how easy it is to put it on the screen. And if you look close at this section here, and you like watch one wave as it hits the surface, it's going fast, and as soon as it hits the thicker surface, it slows down. And the rest of the wave continues to go fast. So you see this weird warping of the wave. And then once the rest of it gets into the material, it's back to like a normal straight line. But right here, where one is slow and one is fast, you get this warp, this bend. And it gets more pronounced the more the angle changes. So we get less warping when we are hitting it almost directly. And the more we angle it, the more warping happens, the more that it bends. So what else? So here's just an interesting example one more time, why it can be so hard to learn how to like spearfish. You think you see a fish, you throw the spear at it, and you miss it high. And that's because the light, so first of all, for you to see the fish, light has to be coming in through the water, it has to bounce off the fish, and then it has to move up to your eyes. And the problem is the light, as it bounces off the fish and goes towards your eye, it has to go from the water to the air. And so this is just like in the simulation, as the light comes up, this corner hits the air first, it starts to speed up because the air has that lower index of refraction. And so the left side goes fast and the right side goes slow. So once again, we get one of these and it bends. So once it's all the way out, then it just goes up to your eye. But your brain is not trained to like account for this bending of the light. Your brain is trained that when the light comes in at this angle, your brain extrapolates that it's the object that it's bouncing off of is right here. This is like an automatic response that our brains have evolved to do over millennia. So you have to like actively think, aim under, because the actual fish is down here. It's pretty cool. And this can lead to all sorts of cool stuff, like when you go to the zoo and you see something like this. You have thick 4-inch reinforced glass. You have a lot of water. And so you have light that's traveling just through air and the glass up here. But then you have light that's traveling through the water and glass over here. And it can lead to these crazy looking distortions. So if you want to have fun, do a Google search for refraction examples, and it will blow your mind. I think that is everything. This would be some math that we would do, but we're not going to. So your assignment is some CASA learning questions. Some of them you're going to need your reference tables. Good luck. Let me know if you have any questions. Have a good weekend. Take care.